Hello, everyone, and a very good afternoon to all of you. Welcome to our webinar on quality assurance for artificial intelligence and machine learning. Today is the 8th event organized by WWT Women Who Test Bangalore chapter. I am Shivalika. I am part of the WWT community, and I represent Trigent as a customer success advisor, and I'm basically responsible for QA and testing services. I'm very excited to be your host today. And just to get started, I'm sharing my screen. I'll go to the next screen now. Yeah, so just to give you some background on WWT, Bangalore chapter, Women Who Test is a great platform for women, women professionals, especially who are, in the testing domain. This is a platform where all of us can share our experience and learn from each other. Trigent, just to give you a quick introduction about our company, we are a 25-year-old technology firm, and our value proposition is really around helping companies overcome the limits of time, technology, and budget. And I'm also excited to let you all know that we recently won an award for the best project for agile testing, and this was at NAST Award 2020, North American Software Testing Award. Now just getting on the key topic for today, the key subject, for the webinar today. As we all know, AI is, of course, a very interesting topic, which is transforming businesses everywhere. And the main challenge for now, I think, for multiple organizations is, having, testing these applications. That's the key challenge. And that's basically because of the lack of having a standardized approach to do it. So with this, I'm really pleased to welcome my special guest, Mukund Kannan, who is the Global Competency Head AI at Tech Mahindra, and he has successfully established a Center of Excellence for AI from the ground up. He's a tech veteran when it comes to the IT domain, and he has about 30 years of experience in the IT industry. With this, welcome Mukund to the WWT community, and without any further ado, I would hand it over to you. And yeah, over to you. The stage is all yours, Mukund.
Yeah, thanks, Shivalika. So you're going to pass on my pass on the presenter rights to me now?
Yes, Mukund, I just did that.
Cool, yeah. So I'm assuming you're able to see my screen, all of you. You can see my screen?
Yes, Mukund.
Cool, yeah. Hi, everyone. Thanks, Shivalika, for the introduction. I am actually going to just talk about quality in general, about artificial intelligence and projects which are around machine learning. Yeah, so probably just explain the difference between AI and ML, but I'm not going to be restricting myself to doing only testing or testing related to AI. I'm going to talk in general about what quality means to a deployed machine learning project. Yeah. So before we just get started, I'll just set the context in terms of what is AI and what is machine learning for those people that probably have a little bit of confusion. So artificial intelligence is a very large technology domain that contains a lot of different approaches to solving one problem, which is to emulate the computers do the same things that the humans do without much of seeming effort. Yeah. So it's been around since mid 50s, and in the last 70 or so years, we have come through a long way in terms of trying to basically crack that problem. And the latest approach to solving that problem is what is known as machine learning. So my focus is machine learning, and when I say artificial intelligence, I mean machine learning currently. Yeah, that's basically the most predominant way to crack the AI challenge. So what is machine learning? Just to set the context as to what is machine learning, I'll just take about a minute or two to explain the machine learning concept itself. So machine learning is actually, the traditional approach to getting the computer to do anything is to break down a problem statement or how to solve a problem into, steps which are going to basically get executed by the computer towards achieving the objective, which actually worked out very well for us in the last 30-40 years. But if you really look at some of the challenges that we are not able to do, for example, we can't actually describe how to identify a face. That's not actually within our cognitive ability to put down a description. Yeah, the description, when we are not able to do, we will not be able to actually break it down into tasks and program it. So that's one challenge. And then secondly, there are challenges that we actually encounter in the real world, where there are multiple dimensions that go into making a decision, and that is actually going to end up uh, limiting our capability to say, okay, this decision was taken because of a combination of these different parameters. And so when we are not able to even keep all those parameters in our mind, we'll not be able to describe a problem and actually, describe very clearly as to how to solve the problem. So I mean, if you just keep that in mind, and when these two are the main aspects of why we are actually getting more and more into the machine learning world, where what we're really trying to do is that without actually getting prescriptive about how to solve a problem, we're going to actually just show the computer, show a learner program the evidence of having solved a problem, right? What I really mean is, I'll try to take an example and explain it. When I'm actually going to identify from a picture it is a cat or not, right? I can actually just the traditional approach would have called me to kind of describe that in great length, saying a cat is actually a furry animal, and it's got pointy ears and whatnot, and it's got like it's got a mush and all of that, and it's got a nearly round face and all that. And but obviously most of these descriptions are very extremely inaccurate, and they'll fail for more cats than we would ideally want, right? So instead of that, if I can show an evidence of having identified a cat, and evidence of having rejected another picture which didn't have a cat, and if I provide sufficient evidences of that, a program which has got an innate ability to look for those patterns that match the evidence, will be able to actually figure out what patterns really end up making a cat or not a cat from a picture, right? So this is very rough up, accurate, inaccurate way of kind of describe machine learning, but it is actually a good way to keep in mind when we are talking about machine learning. So machine learning is about getting a program to learn from evidences or data, and actually let it formulate a pattern of how a prediction was made or how a decision was made, and that's basically machine learning, right? So just kind of drive a point here. If you look at it, the traditional approach is that we write a program and we actually just go ahead and provide data. What I really mean data is that, take another simpler example of house price prediction, right? So you will end up having a program which will say, wherein we would have actually broken the decision-making process into multiple steps. We'll say if there are 3 bedrooms, it will cost you this much. If if the square feet area is this much, you basically have to use a multiplication factor of this much, which is basically the square feet area per square feet area cost. And then if it's got a premium location, then there is an additional cost of this much. All of that would be described, and a computer will follow through the steps to finally identify, given a data. And the data, we will actually provide the number of bedrooms, number of square feet area, the square feet area, and then basically whether it's a premium location or not, and it will use that program and follow through to give you an answer of what is the final price for that house. Yeah. But the reverse of approach, so in this case, I'm actually giving a program, I'm giving the data, and then the computer actually uses that and gives you an output, which is basically the price of that, the new data that you supply, right? But in machine learning programming, you're going to do it the other way around, right? So we're going to basically take, as in the similar approach, we're going to end up taking a lot of samples of data where we are going to say so many, number of rooms, square feet area, and whether it's premium or not, and then the final price is also given. So if you give a lots of data containing this information of having gone through that and decided the price earlier, this is historical data, and we basically supply that along with the output. Output is basically the final price, and these three parameters going into that. So this computer is going to basically just go through this and then formulate a pattern out of it and say, hey, actually, this seems to be the weightage, this seems to be the multiplication factor that I need to apply to arrive at this particular price for each one of those line items, right? And that's basically going to give you the same program that you would have written otherwise here. So that program is basically what we call as a machine learning model. Yeah. So the machine learning model is an output of this combination of input that we give, whereas in this case it would be the reverse. So it's nearly a reverse engineered approach to what we are traditionally used to in the programming world, right? So once this program comes out, you're going to end up doing it the same way. You're going to give the program, which is basically a model, and you're going to give the data, and it's going to start predicting. It's going to start going to give you the price of any new house that for which you want the price for. So this is basically how machine learning is, machine learning models are created, and so it's actually a slightly different process. So it's a reverse process to what we are normally used to. Yeah. I'll just give you a slightly more complicated example of this. So let's basically assume that this is a loan prediction example, right? So in this case, what we are doing is that we are taking a historical samples of having somebody, some subject matter expert decided whether a loan has to be given or not. So this is basically the data that comes out of that database, right? So if you look at it, finally, this is the last column is the one that's going to show whether the loan got approved or rejected. Yeah. So no is rejected, yes is approved. And this is the data that goes with each one of them. So in the first one, it is male and whether it's married or not, all of that is there. And then for this, for some reason, it got, loan got rejected, right? So second one actually got approved. So if we can even start making guesses as we go through that as to why a loan got approved or rejected based on certain factors, right? But as we go down, more and more data gets added, some of our assumptions actually will start getting corrected, right? So for example, we might actually just say a very simple random truth in the first one saying, hey, any male loan is going to get rejected, any female loan is going to get approved based on just the, this thing. We can ignore rest of the differences. Then we can actually add the third one and say, hey, that's not true because this second example of male actually got, so we have to look at what is the difference in the data between these three, right? And then we'll actually correct. So think about it as a step-by-step approach to kind of figuring out the logic that goes into making whether this loan has to get approved or not, right? Actually, that's a good enough kind of experiment to go through to figure out what happens in real world machine learning model building exercise, right? So at the end of the day, this is what happens, but most of the real world examples are not this simple, right? Here you have roughly about 11 attributes that goes into this final decision making, but a lot of our real world problems tend to have a lot more attributes than just this toy example that I'm showing you. Yeah. So the complexity comes in the fact that we cannot, as humans, cannot keep more than 3 or 4 dimensions or attributes in mind when we make a decision. So typically we resort to a level of approximation and say, hey, actually ignore these other factors, or basically combine some of the factors and then say, I will make it easy for myself to keep it to 4 or 5 attributes and then make a decision based on that. So that's going to be my best guess. But with computers, that's not necessary. You can ask it to include every single parameter and then come up with the best optimum prediction for that. So that's basically your machine learning model that's going to come out of it, right? So I won't have the time to actually walk you through the whole 9 yards of how machine learning models are built or describe the technologies behind it. But just keep that in mind. Maybe some of the aspects will get clearer as we go about it, right? So there are two steps typically. One is the machine learning build step, and the second is basically the using that model, we'll start predicting the result for the given data. So the first one is called learning, and the second one is called prediction. Keep this, the fundamental principles in mind for us to kind of go with it. So what is different about machine learning, right? So the thing is, there is no coding, there is no design, etc., typically, right? The core functionality of having to predict whether a loan has to get accepted or rejected is not broken down into tasks like we normally ended up doing earlier. There is no real database lookup where we are going to say, hey, actually just put this particular attribute, just look up the attribute and then make a call based on what that attribute this thing. There is no RDBMS behind it and all that, right? So it's all actually seems to be done or learned in one step, and then prediction happens in one go. So there is going to be one line code that you're going to invoke, which is going to probably do thousands of lines of code in the traditional approach. So that will look like pretty much a magic, yeah. So the whole development life cycles will look pretty much like completely driven by input data. So as I said, the learning happens from the data that was given. So in the previous the previous screen, when you saw actually that the model got built from the data of whatever samples that I showed, which is probably around 35-40 samples I gave. Typically, you'll end up supplying thousands of samples like that, and the machine will end up learning from it. So the primary thing that you really require for building a machine learning model is actually input data, yeah, and it just seems to have to get continuously learn from the data as one sample after another, and then correct its assumptions in terms of how to do what the sample shows, how to the whatever results that come in there, yeah. And I'll come to the decision boundary thing later, but one thing I just want to kind of tell you is that even with the 11 attributes, right, the number of possible combinations is very many. The number of possible combinations might be in millions. It might even be hundreds of thousands, if not millions, right? So it's impossible for us to collect all the combinations for us to have a most perfect program which will give you the right answer in all the scenarios possible, right? So we are going to end up having to approximate most of what we are going to do based on the amount of data that we're going to end up getting, right? So in machine learning, it is one of the things that we have to keep in mind is that we are going to have to make a very generic assumption that the input data is a very small fraction of what is available out there in the world for solving that problem, right? If you end up getting 1%, if you get data that covers 1% of all possible scenarios, you have a fantastic amount of data, right? So, but the other flip side of it is that the model that you built is made from the data, and the model, you can pretty much say that it hasn't seen 99% of the scenarios out there, right? Which means that it's a large number of scenarios it hasn't seen. So it has to really learn to generalize from that 1% so that it can actually give the best result for the other 99% of data that it hasn't seen yet. So this is actually one of the most important concepts of machine learning. So in reality, so what we will end up doing is that while we are going to actually end up learn from that 1% data. So let's basically go back to some absolute numbers. So let's basically assume that we have 100,000 training examples from where the model got built, or the machine learned to solve the problem. It is going to end up actually just have to make an assumption that some of these examples are probably not representative of it. So it will make a balance saying, okay, I've had to generalize for the 99% of the things that I haven't seen. So it will actually make certain corrections in a way that some of the examples that you saw are going to fail when you run it again, right? So generalization is going to be an approximation of the data that was given to us with a view of extending that for the unseen data which is out there, which we have to anyway solve without having seen before, right? So that's basically generalization. Humans are very good at it, but the machines, teaching the machines is a big challenge. So what happens is that the decision boundary, what I really mean is the decision boundary is that the yes to no boundary, where whichever data actually flips it over, given a data set from data set from moving from a yes to no, is the decision boundary, right? So that's actually a very vague concept. So it's actually it's going to fail a few things that we would not normally would have expected in the real world. So that's something that you have to keep in mind. I'll just have to rush through to the meat of the matter, but just keep this in mind that there are going to have to be 3 steps when it comes down to taking building getting data, building a model, and actually just deploying that in a live system, right? So the first one is called data pipeline, second one is called model pipeline, and the third one is called deployment pipeline. Pardon my spelling mistake. So these are the 3 steps that we are going to end up seeing, because under the current technologies that we have, these are 3 distinct elements when in a data science lifecycle, right? So as you can imagine, the model build seems to be like a magic, because I just have to go ahead and supply some data, and it seems to magically create, or basically intelligently create the program, and then then it just throws or spits out a model which I have to deploy and start using. So net this step might look like magic, but the effort of making this step work is basically going into the data management, which is going to take significant amount for us effort to kind of set the data in a level where the model will be easier to build. Yeah, so 80% of our effort goes into data management step. So I'll just park it there. But now I'm really going to talk about what is quality in terms of AI machine learning, right? So in the traditional sense, the machine learning, the quality is actually, we can easily define it as the functional aspect, functional and non-functional performance of that particular program, right? So you certainly have certain measures, you have certain test cases, you want those test cases to pass, and you're going to say, as long as it passes so many test cases, as long as it produces as long as the defect count is actually within this particular profile, I think we can certify that as to be a good program to pass it to the next stage. So that is actually applicable even here. So you certainly have to test the functional and non-functional aspects of it. But apart from that, there are few other idiosyncrasies that you have to take into account when it comes down to machine learning, right? The first one is fairness. What I really mean fairness is that you saw the example that I touched upon, which is the loan approval rejection thing. The model has to be fair and in a non-judgmental way, right? So probably we'll touch upon that when we really elaborate that. And it has to actually not show any kind of a bias towards any particular group. So that's actually fairness, right? And then the security considerations are very important, because I think given that the life cycle that we have taken to build the model is very different from what we are used to, it's something that we have to really keep in mind, that there are loopholes within that through which actually a malevolent actor can potentially cause some mischief. So that is something that we have to keep in mind through the thing. So these 3 things largely, apart from privacy related thing, which I'm not touching upon here, will actually give us a measure of what how to kind of say whether a model is a successful model or not. So what I'm really going to touch upon, what I'm going to do is that touch upon each one of these areas, and I'm not going to be prescriptive saying, hey, actually this is how you have to do. I'm just going to throw in some generic ideas out there for you to build upon it going forward, right? So that's basically going to be my approach. I'm not going to be prescriptive saying this is how you have to test, this is how you have to basically look for issues and all that. I'm just going to throw in some ideas, because most of these things are actually just evolving areas, and so I'm just going to restrict my discussions to top level points. Yeah, the first one is actually the functional validation, which is the traditional testing, right? So the testing is actually the machine learning testing is going to be different as compared to the programmed software that we typically end up testing, right? So the first one is actually task based versus decision based. So just to go back to the example that we took, if somebody told you here is the data, this is how the machine, let's say the ML model got built, it becomes your job to actually try to understand or come up with certain assumptions as to what the model might end up having, right? Or you have to actually get into a kind of a interview session with the subject matter expert who has to tell you, okay, this is basically how it had happened in the past, and this is basically the result, right? But in the older world, somebody has already done that and actually given you those tasks broken down so that you can actually use that as a basis for you to build your test cases, right? So a bit of a data science background is required for anybody to get involved in AI machine learning, life cycle going forward. Which it is not restricted only to the data scientists or the machine learning modelers or ML engineers, right? So it's actually going to be for everybody. So you need to start thinking in terms of, okay, here is the decision that has gone taken that I see as having been taken using a sample set. What could potentially be the decision making problem, which is very difficult, which is where the challenges of why we challenges have come. That is exactly why we even embarked on this reverse engineering approach of doing machine learning, right? But I think you need to actually walk in with a clear idea that you're gonna be basically meeting a very different challenge as compared to what you were doing earlier, right? So I actually told you a couple of things when I spoke about it. So when I spoke about how a machine learning model gets built, right? So typically a very, very small fraction of data, real world scenarios are addressed by the data that from where the machine learning model got built, which means that there is going to be manual follow-ups, which is going to be, something that we have to be able to, predict and address. So any system that is any model that is going to get deployed will have to factor in for those manual follow-ups. Yeah. So any decent data scientist or machine learning engineer will actually build a model with a high level of skepticism that there are areas that we haven't seen, and then the safeguards, the guardrails have to be built for addressing those scenarios, right? So just very let's just take a little different example here, right? So let's assume that we are going to end up deciding whether something is a defective part or not coming through a shop floor, right? So at that time, we have to actually, let's say we have a model which actually ends up predicting it. So the machine learning ML engineer would have actually just gone ahead and built the model, and actually some of the metrics would have been given saying this model is 97% accurate, which means that in the samples with which he built, it actually performed okay for a 97%, and it failed for 3% of the for the data that it built with, which was acceptable. Okay, but the deal is that 3% still has to be processed separately using a manual intervention, so that we are able to actually get as close to 100% accuracy of the overall process, right? So that is something that we have to be able to do as part of the overall solution. So while it is not a job of the machine learning model to be 100% accurate, the overall system that we end up delivering to the customer will have to be as close to 100% as possible. So that is something that the quality person has to actually end up looking at. Then the trust issues. Typically, business ends up having this challenge, which is they had been doing traditionally in one way, and now we are actually introducing a system, and the system has to be going to end up doing something that they take the same quality, or take the same example, that loan prediction example, right? So any subject matter expert or any business person that had been doing that loan approval rejection process will be very skeptical when it comes to his or her job getting replaced by a machine, right? So it's actually something that we have to address, but how we address is also part of the overall success or failure of this system, right? So that is actually a thing that we will probably just talk about when we come to business acceptance testing. And live systems are not live as in a traditional program approach. We just create an executable, put it out there in the production. As long as we are not adding anything on top of it, it will run for the same scenarios. But that's not the case with machine learning systems. They tend to deteriorate over a period of time for various reasons. So as a quality assurance engineer, it will be your job to kind of ensure that that thing gets addressed properly, right? So that's actually part of this testing process. So let's touch upon some of the things in the data science lifecycle, right? The testing aspects. So the first part is data pipeline, which I actually showed those 3 boxes. The data pipeline testing is it's been around. I mean, we have been using big data analytics and business intelligence dashboards and stuff like that. So that part required us to have somewhat clearer or cleaner data for us to use. And so what we ended up doing through the process was we also figured out how to test and measure the quality of the data. So that is actually not something that is very new currently. Where the challenges are on the next 2 steps. The model building side, when we actually learn to do build a model, we are also taught to do the testing in the same step, right? So if I get about 100,000 samples of data from which I have to build a model, I will break that into, say, 90,000 samples. I'll take that to build the model, and 10,000 samples I'll keep aside as a test data, right? So I will actually just see how it performs on unseen data, which is actually the most important thing. Like I keep repeating, the model has to perform for unseen samples, because as I keep repeating, there are more scenarios that are out there. There are more data that is out there that model is never going to see till it actually encounters it for the first time. So the measure of success is how well it handles it. So we keep this 10,000 separate. So when we do the model build, we'll immediately follow it up by testing it with the 10,000 that it has not seen, and then measure the success of the model using that, how well it performs in the 10,000, right? So that is actually, in one step we will do that. So it's actually not something that we'll worry about. But actually the aggregate statistics that we use to measure success. So there are like certain metrics that we use called area under curve, F1 score, and all of that are aggregate values. So what I really mean is that this 10,000 samples that I used for testing, how well it performed in it. So if it comes down, say 97% of that actually gave the results which are in line of in the same lines of what we expected originally, then we say, okay, good, this is like 97% accurate model. But there is a good possibility that the 3% it actually failed are the ones, all of them actually come into the same category. What I really mean is that if I take the loan prediction examples, it might actually just perform 97%, but the 3% it rejected all happen to be one particular group, right? And if you let that model go to production, then unwittingly you would have actually just delivered a model which actually is going to fail for that one particular group. So we need to really get into the details of that and actually do. So aggregate values are while they give you a good measure, actually you need to do a little more deep dive into the real results to an extent on a sample basis, at least to see that it performs properly. Business acceptance testing is a very interesting thing for machine learning models, and that is actually, as I said, the trust factor comes in. So we need to use that as is where we are going to end up actually getting people to, the business to actually just look at it and trust the system. So that's actually a very important area. We provide certain cool tools to kind of, play around with the data, try to flip it over from one decision to another, and then the business guys will normally end up having some kind of an intuition over a period of time that it will develop, and they will say, okay, I want to actually just increase the salary a little bit, and ideally it should actually now approve the loan. And as long as the model follows their expectations, they'll be happy with that, and that's exactly what you would end up going through in the business acceptance testing. It's going to basically be somewhat different from the traditional business acceptance testing kind of scenarios, but I think the tools will be different and the approach will be different, so that we will be able to use that particular step in the life cycle to develop a level of trust for the model with the business. And then this next one is, like I said, most of the scenarios that it's going to encounter in the real world are going to be very different from what it learned from. So we need to actually just slowly ease in the model into life system. It's not like going to be just deployed on one go. So we have to do A/B testing, canary testing, and all that, and just see how it performs for us, in a randomized tests, and then see how it, and then basically take it from there. So drift is something that is very unique to a model. So that is something that we probably have to look at it as well. Drift is basically over a period of time, the model's behavior starts changing, and we have to handle it with samples and see whether we want to take care of it. So that's actually something that the quality engineer has about as well. So there are multiple tools in there. I'm not going to touch upon it. But I think there are different areas have different tools, but these tools are all evolving. I mean, some of them are really rudimentary, some of them are somewhat mature, but I would say this area is actually, the whole machine learning world is actually maturing, and the tools are also maturing along with it. So I'll just skip this and move on. Okay, so the next aspect that we're going to cover is, fairness. What is fairness? Fairness is actually just ensuring that the model behavior is not in tangential to what we believe as fair, right? A couple of examples that I have here, for example, right? So if you see, Apple ended up actually having some issues, and Wozniak ended up commenting, but in reality, it is actually more to do with the data that it actually the model got built from. So the model ends up having, the behavior comes from the data, and if the data itself actually had the wrong behavior to start with, it will end up learning differently. So Tay is another example, which is a fantastic example. This is a chatbot that Microsoft built, and they just opened it up to the real world, saying, okay, you can start interacting with this chatbot, and the chatbot will actually start learning with each interaction. So they had a automated feedback loop to learn from it, and within about a couple of hours, it really ended up getting to be a real problem, and then Microsoft had to take it down. The problem was actually there were malicious actors who were actually just stepping in and started having a very racist conversation. So the feedback loop actually provided that as a real world, this is how it should do it, without actually having any kind of an ethical consequence, and it just started assuming that that's the real world. That's how the real world is, and then started becoming more and more racist over a period of time. So things like that are actually, that we have to be really careful about, right? So what is, the fairness, very rudimentary definition is that no particular group should be favored as against other groups or other group. Yeah, no single group should actually be disfavored as compared to other groups. So that's basically a simple definition of fairness. So we just don't want it to be biased. Okay, when I say bias, we are talking about unfair bias, right? And then there are different ways to, obviously when we are trying to be prescriptive, because we have to develop models, we have to measure everything so that we can say something is biased or not. There are definitions that will come in as well. But anyway, coming to this, we have to also know where the bias comes in. So the bias comes from, we all have been told that multiple times, that the bias is implicit in the data that it learns from. So for example, the loan prediction thing, it might be that particular data that came from that bank or the branches might have actually been leaning away from giving loan for a particular group, yeah, for a particular minority group, or they were actually little reluctant to give loans for females. If we end up actually having that kind of a thing embedded in the data, the model might end up having. So, and in some cases, it might be, it might actually come from having gone through a bit of a user interaction issue as well. For example, it might not be a very direct overt bias, it might be a linked bias, right? So for example, somebody who happened to be in a particular place happened to be poor, that doesn't mean that every person that happened to be there is poor, right? So that kind of a thing is also there implicit in the data. Even if you remove that area, it might actually still have the bias actually linked to the data, because you are leaving the a few other tidbits there which are going to point to the bias. So anyway, so I'll just the historical bias. There are other things that end up actually getting added when you're aggregating data. You might actually, when you're aggregating, depending on how you aggregate, you're going to end up adding bias and all of that. So there are different things that we end up going through the cycle when we collect data or when we put together the model, and that introduces a bias in itself. So there are different ways to measure bias, but I think just to give you a very quick view, see, demographic parity is one, which is basically going to be if you slice and dice the data into particular groups, no group should actually be disfavored as against this thing. For example, if you take a sample set of predictions that came from, it is not applicable only to ML models, but in general, even courts use this as this thing to see whether there's bias or not. If you take the predictions that came and this, the wrong predictions that came out of that particular process cannot be tilting way towards a minority group, right? If as long as the failures are within 80% of them, are only 20% more in less than 20% as compared to the majority, then we can say it is not that biased. But if it is more than 20%, then I would say, I think there is, not I would say, the courts typically tend to look at it as a biased decision. So that is something that these are very rough measures, but I think these are actually well accepted measures across. Equalized opportunities is given that there are say 100 applicants, and out of that 80% are majority and then 20% are minority. And if you make the selection, if you really need 10 out of that 100 to be selected, then you have to actually go for 8 people from there and 2 people from there, depending on the original proportion of applicants. Actually, it is a very rough estimate, but this is another measure. So there are few, and then unawareness is if you ignore that particular, for example, gender is the thing that we want to use as a yardstick to ensure that there's no bias. If you take that model that has been predicting and completely take out that particular attribute of from the decision, and the model performance should not significantly change. So if you can get that, then you can say that model is an unbiased model. So there are certain ways to kind of measure it. If how well a model performs is actually something that we can do it. But again, one thing I'll say, each one of them are independent of the other. You can't have a model that will satisfy all of them. That is something that we will have to decide upfront, saying, okay, I'm defining my, for my system, this is the measure that I'm going to use, and stick to that. So there are different approaches to making the model fair. I think some of them are actually little in depth because most of them are related to statistics and all of that. But I'll give you one cool one, which is basically the GAN based one, which is the latest one. What we really end up doing is that we take a model which is predicting something, and we create another model that sits next to it, and it is going to guess which is so let's assume that gender is the one that we suspect as the model is biasing the predictions with, right? So we take another model which is going to start guessing which is the attribute of the 11 attributes that we showed in that loan prediction example is the one that it's biased with, right? So this second model will say, hey, actually I think your you are biased based on the gender model, right? So the first model now will basically make some changes to the model and then try to make the second model believe that it's not able to pinpoint that gender model, right? So the back and forth that happens between these two models will make the first model, which is the output that we want, become more debiased as compared or unbiased as compared to originally if we had left it as this, right? So that's actually a cool thing that people are playing around trying to remove bias. So I'm just run through because of paucity of time. So the secure practices are actually the next important aspect, because as I said, the security is actually something that we are taking more and more seriously, because these models tend to now start creeping into real life, life or death scenarios, right? So the one that I have on the right hand side is the Tesla one, which actually ended up making a mistake of the model actually ended up looking at the bottom of a truck and said, "Oh, that's actually an empty space," and try to run through it, right? So that's actually that is something that we have to worry about. So in real life, the more models get introduced, more serious they get, and actually not all of them are mistake because the models were actually trained wrongly or something. In some cases, it might even be that a malicious actor might actually have introduced some of that, right? So how does that happen? The starting point for most of the machine learning is not every time we get fresh data for that and then start. We take a model which was pre-trained for a different reason, and we actually even start from there. So that those are called transfer learning examples. So if you take a transfer learned model, or basically the basic model from where we are transfer learning, these are available out there freely for various things. And if those actually end up created by a malicious actor, they can actually very well go embed something in there and then say, actually, anybody that uses are going to end up having, or they can even introduce attacks. I'll give you one very simple example. This is actually one of the bigger worries in the computation world, right? So just take the one on the right hand side, the top right hand side, this panda, yeah. So you see a giant panda to start with, and then we add some noise to that. Noise is basically some random pixel changes to that, and then actually it produces something again on the right hand side. You see, it looks like a panda for all practical purposes, right? But then that prediction suddenly changes from panda 100% confidence to American black bear. Yeah, I mean it's still a bear, so it's not a big loss, but think of just see the one at the bottom, right? So you see the one on the bottom is a stop sign, very clearly a stop sign. Any human will not make the mistake that it is something else. But we put some stickers. You see those 4 stickers that are put in there, right? With those 4 stickers, we can make the model believe it's something completely different, right? And the scary part of that, you can design you can design the introduction of these stickers into that board in such a way to make the model believe it is whatever you want it to believe. It might actually even believe it's a fish, or it can believe that it is a 100-kilometer speed limit board, right? So if you can actually make the model without even touching the model, if you can just make the model believe that to be the case, then I think we are going to end up having a serious challenge. And these are not made up examples. This is a real example where I think this became a 55 or 55 mile speed limit or some such thing. So so these are actually things that, since it's all mathematics, since it is all actually decision boundary based changes, we can actually find out where the boundaries are and make certain certain very intelligent decisions to cheat the model, right? So how do you make the models more robust? We actually make something as simple as just introducing more noise when the model gets built. That actually reduces the accuracy of the model, but it makes the model more robust. We can actually just go ahead and it won't believe all this nonsense that I showed in the previous thing very easily. It will probably show that it is the American black bear, but the confidence level will be like 20% or something, right? So we can do that, or we can possibly just go ahead and say we can actually have, there are more advanced frameworks like ART framework and things like that, which make the models more robust. Yeah, I think so this actually is a very high level overview of different quality aspects that go into making a model more worthy to go live. And I hope I gave you a view of what it is, and I'm more than happy to take any questions you might have.
Thanks, Mukund. This was a great session, great insights around machine learning based AI. And I see many questions by the audience. We'll just take a few for now in the interest
Sure.
of time. Sure, Mukund. So the question from Ravi is, do we need to test the label data first before testing the predicted outcomes? That's the first question that I see here.
Yes, I mean, as I said, the label data is the one where the model ends up learning from, and a part of that same data set will be used for testing, right? So that is the one that we normally end up using to see how well it performs on unseen data. Without it, you obviously will not take a model. It's like taking a code which was built without going through the testing cycle, right? So it has to pass certain accuracy metrics, like I showed in one screen. F1 score, AUC, ROC, a lot of these things are there. So you will decide which one you want to use, and once those metrics are the success criteria for those metrics are met, then you will actually take it to the real world and use it against real world data.
Sure, Mukund. Okay. A very interesting question from Mahesh. It says, legally speaking, who do you think might be held responsible for the problems caused by ML systems? Would it be developers, or maybe considered as an accident caused by the machine?
I'm not the right person to even answer the question, but yeah, I mean, I think it is a ethical debate that's going on in a lot of areas. There is still no agreement or clear agreement as to who will end up becoming the primary party for that will become liable. Yeah, so that's actually still a long way to go. So I don't think I know the answer for it.
Fair enough, Mukund. The last question for today, which we can take, Mukund, is if we leverage any existing models, example VGG or so, will the testing approach be different?
No, I mean, see, this question is related to transfer learning. So if you are actually going to start off with a particular VG16, for example, and then develop a model, would that be different from starting out the inception and basically doing it? No, the testing side, it shouldn't matter at all, because you are actually testing for the performance of the model overall, and you are actually thinking in terms of the functionality it is supposed to deliver, right? So you can still look at it as a black box model and test it, and you can and you can tend to you can set your success criteria and go with it. So the underneath, what is the where you started off with shouldn't really matter, right? But when it comes to really coming down to the other two aspects that I spoke about, you should actually be worried about it, right? So uh, security side, you have to know if there is any kind of a transfer learned, I mean, the starting point model that they're going to end up having, you have to be able to get some confidence that they are not actually using a malicious model and then starting off from there. That is something that is absolutely important, because if you really look at the machine learning world today, right? It's like a wild world. So anybody could actually just create a model and claim that the model performs well, and they'll obviously supply the data and everything and put it in a lot of places, and people just go ahead and happily take that and start off building on top of it, right? So there are things called model zoos. Then there are, GitHub is filled with these kind of models, and then there are marketplaces available as well. So you can go and get. In most cases, you tend to trust that these models are actually made with the right intent and they perform well, right? And it is very difficult to peer through a model and look for it. It's nearly impossible to see that the model was made with malicious intent. It's not even possible to test it or just look at it and you would know. It's not like code where you can just go through the code and say, hey, actually there is these 4 lines of code that look suspicious. You would never be able to do that in a model. So you would actually have to worry about the starting point, and you have to have some confidence that the starting point is it's a good enough or a secure place to start off with. And then the ethical thing is also equally something that we should be concerned about. So if you really look at the data which we actually build models with, we procure data from a lot of external parties. So for example, weather data is something that is procured from different places. Even loan for that matter, right? So the credit rating is actually coming from credit rating engines, right? And then when you're really looking at it from for marketing, we buy data from the databases that are out there to see the behavior patterns of the users of different websites and whatnot. So these are things that we end up actually procuring, and there is a good possibility that there is some implicit bias in those, or basically bias introduced by the behavior of wherever they started off from. So these are things that have a potential impact on your final outcome, right? So you need to really worry about those two. But testing functional wise, I don't think you should worry about which model this whole thing transfer learned from. Yeah.
Sure, Mukund. I think that's all that we can take on the questions front. Audience, feel free to write to us. Drop us an email. We will get back to you. We'll get in touch with Mukund and get all your answers addressed. And even the questions which we didn't manage to answer today, we will get back to you via an email. And don't worry. So we will be answering all your questions in a day or two. With this, I think we will go ahead and we'll plan a subsequent webinar with you, Mukund, a lovely session. And I must say, I really love this style of presentation that we had today. I mean, it was very unique, and totally enjoyed the session. I'm sure our audience did enjoy as well. On behalf of the WWT community, Women Who Test community, I thank Mukund for spending great time with us, and really appreciate the participation of all our lovely audience today. So we look forward to having another session sometime soon, and we'll keep you posted on this. Thanks again.
Yeah, thanks a lot. I had fun. I hope all of you had too. So, thank you. Bye.
Thank you. Thanks everyone. Bye. Thanks Mukund. Bye.